easily. Okay, so this is the psychometric chart as we discussed in the previous lecture video. And what are those points, what are the different types of lines are there, and each and individual line indicates a particular defined meaning. So what are those meanings of that particular line we can able to understand, okay, from the psychometric chart. And now today we'll discuss on psychometric process. So psychometric process means the different types of process. As you means what is process? Process is something where the state is changed from one state to another state. So the term is for psychometric processes. So obviously there are some state or thermodynamic state or thermodynamic properties of state is change actually from another state of thermodynamical properties. So this is basically state. This is basically process. Okay, means a change of state that at a particular different particular path, that is basically called process. Now, the term is psychometric process. That means psychometric means, as you know, that it deals with the study of moisture air. Now, when it deals with the moisture air, that means for psychometric process, that means obviously there are some process in which you can able to understand, or you can able to calculate or understand actually the change of properties in moisture air or moisture in thermodynamically. That process is called psychometric processes. And psychometric process are there, different types of psychometric process are there. First of all is sensible heating, sensible cooling, cooling and dehumidification, okay, humidification, dehumidification. So these are the different types of 9 or 10 psychometric processes are there. By this manner, by this way, you can able to change the thermodynamic properties of moisture air. But the process is different, vary from one to one. So first of all, discuss on sensible heating. Now sensible heating. Suppose this is the arrangement of sensible heating arrangement in which the air enters of driver temperature, that is TD1, when the air passes through a particular heating coil in which the steam or gases flows are there. So steam or gas flow within the heating coil. Suppose this temperature is TD3, okay, and when the air passes through the heating coil, that temperature is called TD2, means driver temperature basically recorded by swing psychometer, that is called TD2, right? Now when obviously this is the sensible heating arrangement. But what is sensible heating? The sensible heating is that the heating of air without any change of specific heat, that is called sensible heating. So there is no change in specific humidity. Actually there is no change in specific humidity. So this is the specific humidity, okay, this is the specific humidity. So suppose this is the psychometric chart in which you can able to understand that this is the driver temperature. As you go beyond from left to right from your psychometric chart, you can able to understand, or you will able to understand that the temperature or driver temperature increases, okay. And when you go up from the bottom to top directions, the specific humidity will be increases, okay. So when the temperature is increases, means when the temperature is transformed, when the temperature is changed, that means the driver temperature is changed or increases. So obviously one more point, that obviously TD3 greater than TD2. Obviously when this is the heating coil, there are some part of air is contacted with the heating coil, that is there are some portion of air that will be the remaining part of the air that is not partially or fully contacted with the heating coil. So there will be bypasses. So we'll be discussing bypass factor on that. So if the some portion of air of TD1 temperature is contacted with the heating coil, so the temperature after passing through the heating coil of the air, the temperature is basically TD2. Now obviously TD2 means TD2 the temperature of driver temperature, TD3 is basically driver temperature at the heating coil. So obviously TD3 greater than TD2, obviously, because in the heating coil, because some portion of air is contacted with the heating coil. That's why the effectiveness of the coil will be, and basically the air which basically passes through the heating coil, that will be TD2, which is basically less than TD3. Now if you want to elaborate, or if you want to explain your psychometric chart, you can able to understand, okay. You do understand that this is the psychometric chart. So this is the TD1, TD2, TD3. So obviously TD1 greater than TD2 greater than TD3. That means higher temperature means heating coil temperature is TD3, which is basically greater than TD1 and TD2. And now, so obviously it indicates, so TD1 greater than TD2 greater than TD3. So if you, as you know, this is the driver temperature from your psychrometric chart. This is the line, this is the vertical uniform space line that is indicate your driver temperature. So this is TD1, TD2, TD3. Corresponding this line that indicate basically your driver temperature. Suppose this corresponding line, that relative humidity, okay, that is your phi1. And one more point, that in this process sensible heating, no, there is no change or any change in specific humidity. Any change in specific humidity means specific humidity is constant. That means if the process sensible heating process is 1 to 2, that means W1 is equal to W2. Specific humidity is constant, or there is any change, no change actually, no change in the specific humidity, that will be W1 is equal to W2. Okay, so obviously if W1 is equal to W2, obviously it will be a constant line or perpendicular to the specific humidity line and parallel to the driver temperature line. So this is your process 1 to 2, in which this is the phi1, that means relative humidity, and at particular point 2, that indicates your phi2, means relative humidity indicates at state 2. Now as you go beyond from process 1 to 2, that means, as you know, this is the relative humidity line, means constant pressure line, where the relative humidity is 100%. As you go downwards directions, I mean this direction, in this direction, the relative humidity is decreases. So phi1 is decreases to phi2. So phi1 decreases or reduces phi1 to phi2 in this sensible heating process. So corresponding this point, phi1 and TD1, phi2 and TD2, corresponding you get the value of enthalpy H1, H2, corresponding value of H3. Now what is the what amount of heat added during sensible heating, you can able to understand, or you can able to calculate. Now what is the heat added in process 1 to 2? That will be H2 minus H1, from process H2 minus H1. H2 minus H1 will be, also you can also write in this form, CPA into TD2 minus TD1 plus W into CPS into TD2 minus TD1. Now TD2 minus TD1 is basically common here, okay, and CPA plus WCPS, right? CPA is basically specific heat of driver temperature, dry air actually, specific heat of dry air, and CPS, specific heat of superheated vapor. Now CPA plus WCPS, this is basically your specific humid heat, this is the specific humid heat, and TD2 minus TD1 is the temperature difference between driver temperature at the air entry, inlet and exit on the sensible heating arrangement. Okay, and this specific humid heat or CPM, that value is basically 1.022. Okay, so the expression or the heat added during sensible heat process, that will be Q, that equal to 1.022 into TD2 minus TD1, where TD2 is your driver temperature at the exit section of, or you can say that this is the driver temperature of the air when it exits from the heating arrangement or sensible heating arrangement, and TD1 is your driver temperature at corresponding section 1 when the air is entry or inlet section at the particular heating arrangement or sensible heating arrangement. So heat added process in this process will be Q is equal to 1.022 into TD2 minus TD1, or you can say, or you can also calculate directly from your psychrometric chart, that if the process is such that process is sensible heating, so corresponding TD1, TD2, you can, and if you know the value of phi1 and phi2, and obviously in sensible heating process phi1 it decreases to phi2, so corresponding this point you can able to understand, or you can able to easily calculate the value of enthalpy change. This is the enthalpy change, nothing but heat added during the sensible heating process. So you can easily calculate from this value easily from your psychrometric chart. That will be difference between H2 minus H1. Okay. So this is the sensible cooling process. Okay. in which you can see that in the as the psychometric processes, there are the sensible heating already we discussed. In the sensible heating was that the heating of air without any change in specific humidity. Okay, so in this and in sensible heating process, the heat addition takes place, or heat addition process of that is basically from process 1 to 2. That amount basically 1.022 into TD2 minus TD1. The dry bulb temperature difference between dry bulb temperature of section 1 and in between section 2 and section 1. Now in case of sensible cooling, the process is same, because the cooling of air without any change in specific humidity. The cooling of air without any change in specific humidity. That means suppose this is the arrangement, this is the sensible cooling arrangement, in which you can see that this is the cooling coil. Okay, so this is a cooling coil in which the ice or normal cold water passes through this cooling coil, and the air inlet condition temperature that is given as your TD1, and the air exit conditions, the exit temperature of the air, that is given as TD2, and the cooling coil temperature is given your TD3. Okay, so in this case actually the temperature of TD1, TD2, TD3, that will be, if you plot your psychometric chart, obviously TD1 will be very, very much high compared to TD2 and compared to TD3. Now in between TD2 and TD3, the temperature exit section temperature of the air, that temperature is TD2. It will be basically greater than TD3. Okay, it will be greater than TD3 because of same condition. This is because of bypass factor, because of bypass thing. Because there is some amount of air that will be directly contacted with the cooling coil. When some portion of air directly contact with the cooling coil, so obviously the temperature of air, some portion of air will be decreases, but all the volume or all the fraction of the air, actually all the percentage of air, the air will not be actually decreases. Temperature of the air will not be decreases. So there is some temperature, there is some fraction of air, some volume fraction of air, actually temperature will be reduces, but not it up to 100%. Okay, so obviously TD2 greater than TD3 in this case. So in this case, the air exit section temperature, suppose this is your TD2, and the cooling coil temperature is TD3. Now this is a psychometric chart. It is a psychometric chart in which you can able to understand. So this is the psychometric chart. Okay, so this is the dry bulb temperature TD1, dry bulb temperature TD2, and dry bulb temperature TD3. Okay, now as you know, this x-axis basically indicates the dry bulb temperature, and this y-axis indicates your specific humidity. Okay, this is specific humidity. Now as you go beyond from left to right, so obviously dry bulb temperature will be increases, and when you go beyond, when you start from the bottommost position of the psychometric chart, or the right position, when it goes upward direction, that specific humidity increases. So sensible cooling is such type of process in which the cooling of air takes place, but without any change in specific humidity. So without any change of specific humidity, that means in this process the specific humidity doesn't change. That means W1, suppose the sensible cooling process is 1 to 2. So that means W1 is equal to W2. That's a sensible cooling process. Now suppose this process 1 to 2, that is basically sensible cooling process. And as you know, this is a constant pressure or saturation curve line, and relative humidity is 100%. As you go downwards directions, so what happens that the temperature or relative humidity is somewhat decreases. Okay, so as you go beyond, as you go downwards of the relative humidity line, you can see that the relative humidity basically decreases. Okay, so this is your maximum relative humidity. That means that is 100%. That will be 90, 80, 70, 60, 50 like that. So this is a TD1 line, this is a TD2 line, TD3 line. So in this plot, from this psychometric chart, you can able to understand the temperature of air of actually dry bulb temperature of air. So that is TD1 is very high, TD2 is less than TD1, and TD2 is in between TD3 and TD1. But TD3 is a cooling coil temperature, TD2 is your air exit temperature of air, and inlet section of air, that is your TD1. Now this is a specific relative humidity line, phi 1, phi 2, phi 3 corresponding the process phi 1, phi 2 and phi 3. So this process is from process 1 to 2, okay, from process 1 to 2. Now when this line actually driver temperature line cuts with the relative humidity line, suppose this point here, when the driver temperature cut actually in the relative humidity line, suppose here phi 2 line, so constant means constant specific humidity line or specific humidity doesn't change. That means TD1 is changed. TD1, so obviously TD1, TD2 actually less than TD2 less than TD1, right? TD2 less than TD1. So in this process indicates your sensible cooling process, because from process 1 to process 2 indicates there is no change in specific humidity. Okay, this is a constant specific humidity line, and TD1 and TD2, in between TD1 and TD2, it indicates that the temperature of driver temperature of the inlet section is greater than the driver temperature of the air of exit section. Okay, so TD2 is your ultimate final destinations of the air, means the after effectiveness of your sensible cooling process temperature. So that is your 2, and that's the 3 point. So corresponding, if you draw the lines from the enthalpy, you can able to understand, or you can able to calculate the H1 and H2 from psychometric chart or psychometric chart. Okay, now the question will be asked, or question will be in your mind, that what is the amount of heat rejected during sensible cooling process? Because when the air touches the cooling coil, so there is some heat transfer takes place. That means some heat rejection takes place, because in sensible cooling process there is no actually heat addition takes place. So in a sensible cooling process, the temperature of air is basically reduces. Okay, so that will be heat rejected during sensible cooling process. That will be the temperature difference, or as you know, the enthalpy difference between H1 minus H2. In case of sensible heating process, that was H2 minus S1, right? H2 minus H1 was the heat added during the sensible heating process. But in case of sensible cooling process, the heat added or heat rejected, actually heat rejected, that will be, or heat rejection takes place, that will be H1 minus H2, H1 minus H2 against H1 minus H2, that can be written as in this form, that CPA into TD1 minus TD2, right, plus WCPS into TD1 minus TD2, where CPA plus WCPS will be the specific humid heat, and TD1 minus TD2 is the driver temperature difference. Now, specific humid heat, the value is basically 1.022. We already discussed on that. Now, actually total heat rejected during sensible cooling process, that will be 1.022 into TD1 minus TD2. Okay, so this is the sensible cooling process. So as we discussed that what is sensible heating and what is sensible cooling, and what are the process takes place in the sensible heating and sensible cooling. So as we see that for sensible heating and sensible cooling, that temperature of driver temperature of cooling or driver temperature of coil in case of sensible heating process, that is basically that TD2 means driver temperature at the exit conditions from the sensible heating arrangement, that temperature is basically less than the temperature of the coil temperatures when it is used as heating coil. But in case of sensible cooling process, when they are in a cooling coil are there, and the temperature or driver temperature of the exit section of the driver temperature in the sensible cooling arrangement, the temperature is basically greater than the temperature of the cooling coil temperatures. That is basically TD3. So TD2 greater than TD3. But it is not desirable. It is not desirable because if the process is ideal process, if the process is 100% efficient, then it should be for sensible heating process. For sensible cooling process also, TD2 should be equal to TD3. Means driver temperature at the exit section of the arrangement of sensible heating or cooling process, that will be equal to the temperature of the cooling coil temperatures. But that is not happening in the sensible heating and sensible cooling process, as we discussed in the previous topic. Now, what is the main reason behind this? That reason is that bypass factor. Bypass factor is main reason for this. Now, so this is the arrangement. So suppose this is the arrangement. Now, what is bypass factor? First of all, bypass factor is name suggests that there is some amount of, or there is some fraction of air that is basically bypasses, which is not directly connected or contacted with the coil. So there is some bypass. So okay, this is the bypass, and the rate fraction of the factor is called bypass factor. When you calculate this bypass factor amount or fraction for sensible heating and cooling process, you can able to learn about these things. Now, suppose this is the arrangement in which you can see that this is the 1 kg of air, that driver temperature is, as you know, that driver temperature is TD1. So this is the inlet section in which the air entry section are there. So this is the coil. The temperature of coil is here TD3. Now, when the air is passes through this coil, that the air is contacted with the coil temperatures. Suppose this is temperature TD3. So we are assuming that first of all the total amount of air was 1 kg. Now, in between 1 kg, there are x kg, means amount of x kg of air, that is bypasses. Okay, so these are bypasses x kg of air. Now, remaining portion is 1 minus x kg. That remaining 1 minus x kg is directly contacted with the coil. Okay, so this x kg basically, the bypass, right? Because this is not directly contacted with the coil, that's why the efficiency is not 100% of the coil. Okay, now, so this x kg basically bypasses through the chamber, but doesn't contact directly with the coil. So the amount of directly contacted of air, that is basically 1 minus x kg. So this is 1 minus x kg. Now, after passes through the coil, after some time, the exit section will be, total air will be 1 minus x plus x. That will be, after all, total air that out basically 1 kg of air. Now, at that particular time, the temperature that exit, that will be TD2, means driver temperature at the exit section. That will be TD2, and this process is basically done in the insulated chamber. Okay. Now, if you balance the enthalpy equations, so that will, the inlet section of this particular chamber, that will be 1 kg of air is inletted. Okay. So 1 kg, so x kg here, so x into CPM, that means the enthalpy of, for the sensible heating process for the x kg amount of air, that will be x into CPM into TD1 plus 1 minus x kg into CPM, means m. So x indicate here, so m, so mass, total amount of mass, actually what amount of mass are directly contact or doesn't contact. So that will be x CPM into TD1. CPM means CPM, that means the specific heat or humid specific heat, as you know that. So x into CPM into TD1 plus 1 minus x into CPM into TD3 is equal to total amount of air that exit from the section, that will be 1 kg of air into humid specific heat into TD2, because sensible heat, that will be this one. Now, so from this equation you can calculate the amount of x. X is your basically bypass factor. Okay, so in between 1 kg, x kg basically bypasses through this channel, so that's why x indicate your bypass factor. Now, x will be TD3 minus TD2 divided by TD3 minus TD1. Now, for heating coil, as you know that heating coil, that bypass factor will be TD3 minus TD2 divided by TD3 minus TD1. Similarly, for cooling coil, x is equal to TD2 minus TD1, TD2 minus TD1, TD3 actually divided by TD1 minus TD3. So this is the bypass factor for heating and cooling coil. Now you can also able, or you will be also able to calculate the bypass factor for another way. Like as you know that when the air is passes through a particular heating coil, so the amount of heat, the amount of sensible heat is given out by the coil, that QS is also U into AC into TM. So what is U? U is your universal, sorry, So U into AC into Tm. Okay, so universal heat transfer actually, and AC is your total surface area of the coil or surface area of the coil into Tm. Tm is your logarithm mean temperature difference. So logarithm mean temperature difference in your heat transfer chapter, in your heat transfer heat exchange chapter, you can able to learn that what is logarithm heat transfer, or sorry, logarithm mean temperature difference. So Q is equal to U into AC into Tm. Okay, so U is equal to overall heat transfer coefficient. U is equal to overall heat transfer coefficient. AC, basically the surface area of the coil. Tm, that is your logarithm mean temperature difference. Now, so from this, as you know that Tm, so from the, as you know that Tm means logarithm mean temperature difference, Tm is equal to Td2. So this is the plot from the heat exchanger, that Td2 minus Td1 divided by log E into Td3 minus Td1 divided by Td3 minus Td2. So as you know that for heating coil, X is equal to Td3 minus Td2 divided by Td3 minus Td1, but in this expression, that is the reverse. For heating coil, if you calculate the logarithm mean temperature difference for heating coil, so that will be log into e to the power 1 by bypass factor, because this is the reverse. Here Td3 minus Td2, but here it is in the denominator, and in the numerator portion Td3 minus Td2, and that is Td3 minus Td2 denominator and Td3 minus Td2 is in denominator, but in this case numerator. So that's why it's the reverse case. So log e to the power 1 minus bypass factor dTm. Okay, so this is the Tm. Okay, so as you know that Qs is equal to U into AC into Tm. So Qs is equal to U into AC into Tm. So Qs means sensible heat is given out by the heating coil. So that will be, if you put this value Tm is equal to this one, so this expression will become Qs is equal to U into EC into this one. Okay. Now in the previous lecture, in the previous topic, when we discussed that what is the amount of heat added during sensible heating process, that will calculate that is equal to Qs, that equal to Ma. Here Ma, in the previous topic we already considered that Ma here, that is 1. So Ma is equal to, but here we have considered that amount of air that is equal to Ma. So that's why Qs is equal to Ma into Cpm into Td2 minus Td1. So Qs is equal to this one, Qs is equal to this one. If you equate both these equations, Qs, that becomes UAC is equal to this one. So ultimately, when you calculate this bypass factor will be e to the power minus of UAC divided by 1.022 Ma, where BPF basically indicate your bypass factor, U is equal to overall heat transfer coefficient, AC is equal to AC, basically your surface area of the coil, and Ma means amount of air that is passes through the heating coil. So this is the expression for bypass factor. Bypass factor for heating coil you can calculate easily for expression by Td2 minus Td2 divided by Td3 minus Td1, or you can also calculate bypass factor in this manner also, e to the power minus UAC divided by 1.022 into Ma. Okay, so this is the bypass factor for heating coil as well as cooling coil. But one more important point, that low bypass factor indicate that better performance of coil. Very important. Note that point, that low bypass factor, if the value is given out that bypass factor is less, that indicate actually the coil gives you the better performance. If the bypass factor value is high, then what happens? Then the value of, or the performance is roast. Okay, or bad, you can say that. Okay, so these are the, and what is the factor that depends on bypass factor? First of all, number of fins provided. So these are the fin. So number of fins provided in unit length, number 1. Number 2, number of rows in a coil. Number 3, velocity of flow of air. Okay, these are the three dependent, or these are the three factors that depends on bypass factor. Okay, so these are the expression for bypass factor for heating and cooling coil. Okay. So as we discussed that what is the bypass factor for heating and cooling coil. So as you know that bypass factor, so you can easily calculate the efficiency of heating coil and cooling coil. So 1 minus bypass factor, basically your efficiency of heating and cooling coil. So efficiency of heating coil will be TD2 minus TD1 divided by TD3 minus TD1, and efficiency of cooling coil, that will be 1 minus bypass factor of cooling coil. The final expression will be TD1 minus TD2 divided by TD1 minus TD2. So these are the expression for heating coil and cooling coil of the efficiency. Okay, so the efficiency of the heating coil and cooling coil. Okay, in the next lecture video we will discuss on different psychrometric processes like humidification, dehumidification, and cooling and dehumidification. These are the topic will be discussed in the next lecture video. Okay, thank you very much for listening and watching me, and goodbye.